Hello, thank you for watching our video. My name is Gonzalez, manufacturing engineer, Cal Poly.
And my name is DJ Ikeda, another manufacturing engineer. And today we'd like to talk to you about our senior project that we partnered with Cal Poly's human-powered helicopter for their carbon fiber spar machining fixture with a technical advisor, Kurt Colvin.
A little bit of history. The Igor Skorsky Prize was created by the American Helicopter Society in the 1980s, and the basic requirements were be able to fly for 60 seconds, reach an altitude of 3 meters, and stay within the box of 10 by 10 meters, all being powered by the human. On the 1989, a team from Cal Poly was able to lift up for 9 seconds, but after that, no more work was done to win the prize.
Back in 2009, the project was resurrected with a new Cal Poly team, and they started looking into new designs and new materials that they wanted to utilize in their new project. One of the materials that they decided upon was carbon fiber due to its lightweight yet high strength yields. But using carbon fiber posed different challenges for the machining and assembly. And so, talking with the human-powered helicopter team, we came up with a problem statement of what our scope would be in this project. So our problem statement was that a lightweight carbon fiber spars will be used on the wings of Cal Poly's human-powered helicopter. The spars must be accurately machined to specifications, but currently there's no tool to do so. The project team asked for a fixture and tooling to aid in their production. So once we had that problem statement and we wanted to figure out a solution strategy to come up with a successful project.
To come up with a solution for this problem, we break up the problem through 4 main points. The requirements and verification of those requirements. We work with the team and to collect the most data possible and come up with a good solution. And then we create a prototype. After that prototype, we do some testing and discover more things we should improve our tool. Then we come up with our final design and test it again. Finally, we did the economic justification to make sure we stay within a reasonable limit.
And so once we had that solution strategy in place, we started with step 1 and looked at the requirements. We talked with the HPH team, Human Powered Helicopter team, to understand what they wanted from a fixture and what part would be produced on it. They talked about the carbon fiber spars, that they had various lengths, that the hole sizes range from 375 thousandths to 750 thousandths of an inch, and that the diameter of the spar overall could range anywhere from 2 to 4 inches. They wanted a fixture that can handle all that variation as well as be error proof so that any operator can come to the drill and fixture setup, throw on a spar, and run it through and come out with the same quality part each and every time, no matter who the operator was. And they had other requirements to just help the quality and reproducibility of the part. So once we had those requirements from the HPH team, we wanted to look into a little bit more of the methodology and verify some of those requirements, and we did a literature review where we focused on 3 main areas.
The 3 main areas were the fixture design theories, the carbon fiber machining specifications and needs for our project, and the material selection for our tooling and our fixture.
So once we delved into the literature review and came up with some verifications and some understanding of what the processes were going to look like, we developed our first prototype.
This is a look at our first prototype. As you can see, we have a solid bit block with the spar being held by the clamp, a flat clamp, and we still have we haven't find a way of locating the second requirement, which was the length of the pipe. And on our final review, we come up with that solution.
So obviously this first prototype had its flaws. It was a little bit more complex than needed, and just constrained it to places we didn't want it to be. So we moved forward and came up with a new design, what ended up being our final design. The benefits of this final design is we're using 2 V-blocks with a space in between that allows for our new tool, which has an extension on it, So instead of the old tool where they had to go little bit by little bit to expand the hole to the right dimension because of the tendencies of the carbon fiber, we found a new tool with an extension that allows them to drill through the entire spar from one end through the other and keep that location of the hole the same for both parts. We put an end stop that can be adjustable for those different dimensions from the end of the spar to where the hole should be needed. We changed the clamps out to make them less complicated and actually better for carbon fiber machining. So with these strap clamps, the force of the holding is distributed along a greater surface area, reducing the deflection tendency of the carbon fibers, and well as making it quicker and easier just to clamp down the part while still holding and supporting in the necessary ways. Since each part of the fixture is a different component and can be separated, it increases for flexibility for this fixture and these components to be used in different parts and different processes if needed. So with the quicker clamps, better tooling, and even less weight from the material selection that we chose, this final design encompasses everything that we needed. And here's a little video showing you just our fixture and process. So then we also wanted to make sure that our fixture not only just worked, but that it was economically viable. So we looked into the cost and did an economic analysis, and we found that the fixture cost, taking in all the parts that we used, the machining time and assembly, came to about $90, just over 90. And then we looked at the time of the operators machining, using the fixture and not using the fixture. In the first setup, when they were having to measure every spot, each hole, so 2 holes for each part, mark it down, go through many different tools, took upwards of 12 minutes. With the new fixture, they have to strap it in and go down with 1 tool, 1 pass, and reduce the time to 2 minutes. And so it's a total saving of $93 when taken over the span of 14 parts necessary for the human-powered helicopter. So within even just the initial 14 parts that are needed, it does save them money, and with every project there are some parts that need to be reworked or some new parts that need to be made due to breaks or failures from other processes, and so those are all just savings built on top of each other. So with this economic analysis and our final design, we had a product that we were happy with, a product that accurately locates and supports the part during machining, meets our customer requirements, saves money through initial run, and allows for flexibility not only between the part sizes from those spars, but also to be utilized in different projects, which is kind of important as we go on to our next step.
Unfortunately, the prize was granted to the University of Toronto, not Cal Poly, but we feel that our tools will be used for future projects, not just the HPA. It's able to be reused for multiple projects.
Yeah, so although University of Toronto did win and won the $250,000 cash prize, we do think this project was very beneficial and helped us a lot working with the client, figuring out the fixture dimensions, doing the literature review and all that, and we learned quite a lot from it. So thank you for taking the time to watching this video, and we look forward to the Q&A session later on.
Thank you.